Hi, everybody. I am the last talk between you and a snack break, I think. So I am going to ask you to do a quick favor for me, mostly because I'm a little nervous, also because I really need to drink water, and it's weird to drink water when you're on stage and there are people staring at you. So I'm stealing this from my friend Lily Shalene, who has a trick where when she goes to take a sip of water, she asks for people to cheer for her. So if we could just practice that really quickly, Okay, cool. So hopefully that'll keep you awake and me awake, and we'll all have fun. All right, so I'm Stella. Like Courtney said, I'm a tools engineer at Heroku, and we're here today to talk about distributed tracing. I'll be tweeting out a link to my slides. They'll be on the website, so you'll see some links in here and some pseudocode. If you want to take a look, you can take a closer look later on. So let's talk distributed tracing. On my team at Heroku, we spent some time implementing distributed tracing for our internal services. And a lot of the trial error discovery that I'm trying to share here today with y'all was really a team effort. Let's start with the basics. How many people here know what distributed tracing is? Okay, pretty good. Don't feel bad if you don't. That's what this talk is for. How many people are running a distributed tracing system at their company? Okay, this might be a refresher for y'all, but we'll see how it goes. Distributed tracing is basically the ability to trace requests across distributed system boundaries. A simple use case, let's say you run an e-commerce site. You want users to be able to see all the recent orders that they've made. In a monolithic architecture, you have one web process. It's going to return web information with a web request. You might see users who place orders. Those orders have items. Authenticated user will grab all of the orders and items that they have and render it on a page for the person looking at it. Running in a single app, single process. But then you know how it goes. You add a mobile app or two. Those need authentication. Suddenly, things are more complicated. Now there's a team dedicated to maintaining the authorization code. They don't care about orders, so now they have a service. And that could be running in a separate process on the same server, different server altogether. Then let's say we want to also show recommendations to our users for things to buy based on their past purchases. For this team, a bunch of data sciencey folks, they only write in Python, they do a lot of machine learning, and so naturally, microservices. It just happens. But really, the answer is often services. When your engineering teams and your products grow, you don't need to do microservices to find yourself supporting multiple services. And a service in your ecosystem might be written in a different language, might have its own infrastructure needs. And as our web apps in general grow larger, they can start to look less like a garden and more like a collection of different plants in different kinds of pots. And so where does distributed tracing fit into this picture? So let's say one day, e-commerce page that we talked about, it starts loading very, very slowly. And from the perspective of that e-commerce app, you can look at your application performance monitoring dashboard or profile it with a profiling tool, and you'll see your recommendation service is taking a super long time to return your recommendations. And so when you talk about single process monitoring tools, all of these other services in your system look like third-party API calls. You're getting as much information about your calls to Stripe as you are your recommendation service. And so from your user's perspective, you've got 500 extra milliseconds to get your recommendation, but you don't really have any way of knowing why without reaching out to that team, getting access to their profiling tools, digging into their services or having them do it, and it's just going to start getting more and more complicated as your systems get more complicated. And Ben Seligman's got a great quote, is that you can't tell a coherent macro story about your application by monitoring each individual process. And if you have ever done performance work, you will know that people are incredibly bad at guessing where the bottlenecks are in their applications. So how can you increase the visibility? How can you tell this macro level story? Distributed tracing can help you with that. Adrian Cole, another great quote from another distributed tracing person, talks about it commoditizing knowledge. In these increasingly complex systems, you want everyone to have the tools to understand the system without having to rely on single experts for each individual piece. So it's cool. You're on board. You're totally sold. You got some different services. What is stopping you from doing distributed tracing at your company? So there's a couple of different things that make it a little tricky. So for one thing, distributed systems monitoring might be outside your specific language's wheelhouse. So a lot of people in the community are working in Go, Java, Python. So if you're working in other languages, sample code, implementations, they may not necessarily be available to you. There is also a ton of domain-specific vocabulary, so reading docs can be super slow if you don't know what it means. And finally, the most difficult hurdle of all is the ecosystem is incredibly fractured. Distributed tracing is about tracing everywhere, everything. And so as a result, the solutions have to support many different languages and frameworks. And so navigating those solutions to figure out which solution is right for you is not a trivial practice. So how can you get past it? We're going to talk a little bit about the theory, get you a little more comfortable for those of you who aren't, and then we'll take a checklist for going from theory to practice. The basics. Black box tracing is a good place to start. The idea of a black box is that you don't know and you can't change anything about your applications themselves. You would capture and log incoming and outgoing traffic at a lower level than your application, for example, the TCP layer, and you take all that data from your services, send it to an aggregated log, and then using the magic of statistics, you can infer the behavior of your system based on timestamps. But I'm not going to talk about black box tracing today, really, because at Heroku and for other companies, it turns out to not really be a great fit. And so why might this not work? One, you need a lot of data. It can have some delay in returning results because you need statistical analysis on your logs. But the biggest problem for us is that in an event-driven system, for example, if you're doing async jobs like Sidekick, or a multi-threaded system, you can't really guarantee causality. And what does that mean? So there's pretty serious papers written on this topic, but a really, really basic example is that service 1 kicks off a job and immediately makes a synchronous request to service 2. So if you have no delays at all, then your timestamps are going to correlate that story. Service 1, async job, service 2. But if you add some delay into that queue, then your timestamps are going to start maybe looking like service 2 is what's actually making that call. And white box tracing is a way to help solve that problem. It assumes that you have an understanding of the system that you're trying to trace, and in fact, you are actually able to change that system. This is going to be our first test. Thank you. So how can we be sure about that path that's taken? We explicitly pass along information about where it came from through metadata propagation, which is a type of white box tracing. One of the other benefits is that you get latency analysis and troubleshooting in near real time. So we're going to talk a little bit about the history of metadata propagation. Dapper, you may be already familiar with this, especially those of you who are doing tracing today. This is probably the most well-known example of a metadata propagation distributed tracing system. The paper was published by Google in 2010. It inspired the open source library Zipkin, but it wasn't the first distributed system debugging tool to be built. So why was this so influential? In contrast to other research literature on distributed tracing that were published very early on in their development, Dapper actually was published after it had been running in production at Google scale for many years. So it showed that tracing like this is not only viable at scale, but also really valuable. And then came Zipkin. It started as a project at Twitter's first Hack Week, and it was just to re-implement the Dapper paper. It was open source in 2012, and the project is currently led by Adrian Cole. So from here on, when I say distributed tracing, I specifically mean Dapper and Zipkin-like systems, because white box metadata propagation distributed tracing system is really difficult to say. So if you want to learn more about things beyond metadata propagation, you can check out this paper. which talks about some of the other kinds of systems. So how are we actually going to trace our applications? I'm going to walk us through the few major components that power most of the distributed tracing systems. There's a tracer, which is the instrumentation, transport component, a collector, the storage, and the UI. So let's first start at the level closest to your application itself, and that's the tracer. And it's going to actually trace the individual requests. It lives inside your application. It's typically installed using your package management system, like you would install your APM software. And its job is to record data from each system so you can tell the whole story. You can think of the full story of how you go all the way through the system as a trace. This is where our next vocabulary word comes in. There's a span. Within each trace, there are many spans, which make up each chapter in the story. In this case, when our e-commerce app is calling out to the order service and getting a response back, that's a span. In fact, any discrete piece of work, it doesn't have to be a network request, can be captured in a span. So if we want to start mapping this system, what kind of information are we going to send? You could try just sending an ID all the way through in each request, and then you query your logs, and there you go. But you're going to have a similar problem that you had with black box tracing, which is that you can't guarantee the causality based on the timestamps. So we need to create an explicit relationship between each of these components, and you can do that with a parent-child relationship. The first request in our system doesn't have a parent. Parent ID is nil, so we know it's the top of the tree. And then when your auth process talks to your e-commerce process, modifies the request header in that request, and then passes along a randomly generated ID along with the parent ID. Here it says 1, but it could be anything. And it keeps going on and on with each request. And a trace is ultimately made up of many of these parent-child relationships. And it forms what's called a directed acyclic graph. And by tying all of this information, you're able to not just describe this with an image, the system that you have, but with a data structure. And if all we wanted to know were the relationships between our services, if we just wanted to have a map of what our topology looked like, we could stop there. But ultimately, we want to know more about our apps, more than just who's calling whom. We want to know timing information. So we can use annotation to find out more information about timing. So by explicitly annotating when things occur in the request cycle, you can start to see your latency. So hopefully you're not seeing a full second of latency between each of these requests, but just an example. So we're going to zoom in now to the area between where the auth process and the e-commerce process are talking. And so in addition to sending along this trace ID, we're going to send along the parent ID that we talked about earlier in the child span. We're also going to annotate with a tag and a timestamp. And the auth app is going to annotate that it sent the request. E-commerce app is going to say, I've got the request. You can compare the timestamps to see the network latency. So if you're seeing a lot of request queuing, you would see that length of time go up. And on the other hand, by comparing the timestamps between a tag for server receive and a server send, you can see how long the process itself took. So if your app is slow, you'll see the latency increase here. And then finally, you close it out with a client receive to say that the span is complete. Let's also talk about transporting the data now that we've made these annotations. Each process is going to send information via the transport layer to a separate application that's going to aggregate the data. So how does this not add latency to your system? First of all, it only propagates those IDs in band in the headers of the request. And then it reports all of your data out of band to a collector so that that is what actually processes and stores the data. If you use a metric system like Librato, they do a similar system with using threads to make third-party API calls so that it doesn't block your thread of execution. Our data gets collected by the tracer. It's transported to a transport layer, and then finally it's collected so that it can be viewed in the UI. So this is the graph we looked at earlier. It's good at showing your flow of your requests, but it's not really good at helping you solve latency problems. So distributed tracing systems are going to usually use Gantt charts, swim lane charts. Here's an example, similar thing from open tracing, which will show a request tree similar to what we were showing. But if you look at it in swim lane format, Gantt chart format, You'll still see the different services, but now you're able to really visualize how much time is spent in each of those, in the full request and then the sub-requests that make up that full request. You can also instrument and visualize internal traces that happen inside of a service. So this gray section is all something that's happening inside the same service. So you can see the billing service, which is in green, is blocked by the authorization service, which is in red. You can also see that there's some parallel jobs happening inside the resource allocation, which is the gray boxes. And if you started to see a widening gap between those two boxes, you would see that there was queuing behind other network requests. So we've walked through a little bit about what we want. I'm going to show you a little bit about how it's done. It's difficult in a polyglot audience, so I'm going to go from a Ruby perspective and a little bit of pseudocode. So middleware is a really common way that these tracers trace this information. Ruby uses an interface called rack for servers and applications to talk to each other. Sinatra, the Rails framework, they use it. It's a single entry and exit point for all client requests that come in and out of a Ruby application. And rack, like many things, lets us add middleware, so you can customize those requests. So here's some code of our middleware where we want to do some tracing. We're going to have a method called trace that takes a block and traces. So what might that code look like? So our trace method would start a new span on every single request. It's going to record that it's received that request with the server received annotation like we talked about earlier. It's going to yield to our rack app to make sure that the app does what it wants to do and everything happens. And then it ensures that you record that the server send has come back. And the Zipkin source, which I've linked down here, it might be hard to read, is a really great place to see implementations of tracers. And so in the Ruby and Rails world, we can add in the middleware like this and do some configuration to make sure that you don't sample every single request that is in production, because that would be crazy and probably take down your system. So tracing solutions will usually have you do a sample rate. One more. People next door are just going to think y'all are getting to leave early. So you're going to record all of the requests that are coming in, depending on how your language handles incoming requests. And then you'll also want to record all of your outgoing requests as well. This will give you two things. So one, if it's to a third-party API, you'll see that you've made the request to that third-party API, which is awesome. But better, if your next service is instrumented by another team, you would be able to explore deeper and deeper into that request chain. So we can use middleware to do this too. If you're using an HTTP client that supports middleware, it's pretty easy to incorporate tracing there. I'll use Faraday as an example because it's going to be similar to our rack example. We'll pass in our HTTP client app, do some tracing, keep calling down the chain, same as before. But this time our tracing is a little bit different because we're going to want to manipulate the headers. We do that to pass along the tracing ID. So that way, if you're calling to another internal service that you've also instrumented, it's going to be able to see that header, know that it also needs to continue annotating your request. And if the next service isn't instrumented, if it's a third-party call, it's not a problem. They'll just ignore the headers. And so each of these colors would represent an instrumented application. So you want to record that you're starting your client send and ensure that you're recording that the client request was received. Add your middleware, similar to before, and you've traced on both sides. So now that we've seen some examples about how you can do some basic tracing in our applications, let's walk through a little bit of a checklist to talk about evaluating tracing solutions. The first question is, how do you even want to do this? I'm going to give a caveat that the ecosystem is always changing. So this info could be incomplete or obsolete by the end of this talk, and certainly by the time somebody watches this at home. First, should you buy an out-of-the-box system? Sure, maybe. If your resourcing is limited and you can find a solution that works for you, it's kind of like any vendor versus internal build evaluation. It's always kind of hard to say. Lightstep and TraceView are two paid options. Your APM provider might have a distributed tracing option. An open source solution might be a better fit if you have people on your team who are comfortable with the framework and you have capacity for managing your own infrastructure. For us, we have a small team. It's just 4 engineers. We got Zipkin itself up and running in a few months of part-time work while also doing a bunch of other stuff. Partially because we are Heroku and it's really easy to run infrastructure on Heroku. Actually instrumenting each of the applications at Heroku is another task. But actually running the infrastructure wasn't too burdensome. Main open source options were Zipkin and Jaeger. There may be some others, but those are the 2 big ones. What about open tracing? Common misunderstanding is that open tracing is an implementation of a tracing implementation. It's actually an API. And the idea is to standardize instrumentation for different tracing providers. So if you wanted to switch from an open source provider to a paid provider or a paid provider to another paid provider, the idea is that you switch out your underlying package, but you don't have to go and re-instrument your application code. So that's pretty cool in theory because you could switch out vendors without a lot of engineering overhead. So where is open tracing at today? They've published a number of APIs for different languages, but each tracing provider is then responsible for implementing a tracer for each language that conforms to the API. So for example, they published a Ruby API earlier this year, but only Lightstep, which is a product in private beta, or I think it's still in private beta, has a tracer that conforms to that API. So like Zipkin, for example, which already had a Ruby tracer, would need to build a bridge between the existing implementation to the new API. And honestly, interoperability isn't standardized. So if you instrument your Python apps with a paid provider who doesn't support Go, you can't necessarily use a different compatible Go tracer and expect those 2 things to be able to send the same kind of data to the backing service. And another thing to keep in mind, this is true for open source and hosted solution, is that supporting a language is a very variable thing. So at the minimum, it just means you can start a trace in your app like we were doing earlier. But for example, some providers support Ruby, but you still need to write your own middleware for Rack and for each HTTP library you're using. And it's not a deal breaker, but it's an engineering overhead that you may not realize at first when you see that it supports the languages that you're using. And then you need to rinse and repeat for every language you plan to support at your company. And some big companies find that, custom nature of their infrastructure, you may need to build out some of your elements in-house. Etsy, obviously Google, built in-house systems. But other companies build out some custom components and tap into open source solutions. Pinterest's system, which I think somebody is talking about on Friday, started out as an internal Zipkin collector, and then they pushed it upstream. And Yelp did a similar thing, internal Zipkin Python project that they pushed back upstream. And if you're curious about what other people are doing, Jonathan Mace at Brown University published a snapshot of 26 companies and the distributed tracing systems that they use. And even though it was published earlier this year, like all documentation, it is already out of date. And but this is kind of the snapshot of what they found. And then obviously another thing to assess is like, what is your infrastructure requirements? So the tracer and the transport layer need to be compatible with each service you want to instrument. So right now on my team, we're using HTTP and JSON to communicate asynchronously from our apps to Zipkin. But if you have a lot of data and you need to use Kafka as your transport layer for Zipkin, you might think it's compatible with Ruby, but then you realize it's actually just JRuby, and it's very difficult to find that in the documentation until you're halfway through it. So it also might be different than the services you're currently running. So my team runs a lot of Ruby services. Zipkin is a Java service. it's the usual software trade-offs. Another kind of interesting thing, though, is that your tracing system might require a separate agent to run on each of your hosts. So for some solutions, you'll need to have this monitoring agent running, which for us was a deal breaker because we couldn't do that, but it's something to keep an eye out for. Another thing is authentication. You'll need to find out how you can secure who can submit and see data inside your tracing system. For us, Zipkin was missing that piece, which makes sense because that's not their job to maintain authentication and authorization service. So you can run it inside a VPN. But we actually decided to use a reverse proxy to do our authorization. So we're using basic auth for our client posting. We're using HT password to do that with some credentials. It ends up kind of looking like this if you can see it. The client makes the request, NGINX intercepts it, checks for valid basic auth, and then forwards on the request to Zipkin. And we also didn't want anybody in the internet to just be able to see what we're doing. So we also had to add authorization to access the UI. And we used Bitly's OAuth2 proxy, which was really cool. It allows us to restrict access to the UI with people who have a Heroku.com Google address. So when a browser tries to access our Zipkin instance, we check to see if they're authorized. If not, OAuth2 proxy handles the authorization. We're using NGINX and Google OAuth, but the OAuth2 proxy is configurable for multiple OAuth providers and load balancers. So it's kind of nice. But even if you're going the hosted route and you don't have to implement this stuff yourself, you're going to need to find out how are people going to access. Are you going to be the gatekeeper? Or is your team going to be the people like having to generate credentials? Can everybody get access by default? Another thing is sensitive data. There's at least two security issues that we kind of ran into. One is custom instrumentation. It's a really easy place to leak sensitive data. So we wrapped some of our Postgres calls to be able to see in that stack some of the latency that we were having in our database. But if you end up tagging that span with the SQL that you're using, and that SQL happens to contain some kind of PII, for whatever reason, you need to make sure that you are able to see that and you're able to know what happens when data leaks. So this is the case for a third-party provider. You need to be sure that you know how they're going to wipe the data, how long is it going to take. For us, it was easier to wipe our own data, so that was a pro for us for hosting our own solution. And finally, the last thing is, is everybody on board? The nature of distributed tracing is that it is distributed. Your job is not going to end when you have Zipkin up and running. There's a lot of cognitive load to understanding how all of this works, how to instrument your application, and you need to get everybody who's at your company on board to instrument important applications. So set yourself up for success. Don't do what we did. Get it on other teams' roadmaps. Make it a priority. Don't just say, hey, this is a cool thing, and then 6 months later, people are like, what was that thing again? Or just open PRs. Even then, you're going to need to be able to talk about what you did, why you're adding, and be prepared to deal with any latency issues that come across. So this is the full checklist of kind of evaluating a distributed tracing solution. But really, it's this is a lot. So where do I even start if I'm interested in doing this? My advice is if you have free time, if you got 20% time, a hack week, try running Docker Zipkin. It comes with a test version of Cassandra built in, so you just need to get the Java app up and running. You can actually deploy this on Heroku. And this is not a plug for Heroku, but it is pretty easy. And if you're able to get that deployed and the UI loaded, just try and instrument an application that makes an external call, even if it's an API call to a third-party service. It'll help you turn some of this abstract stuff into concrete stuff. It's a lot of fun. So anyway, thank you. If you have any questions, feel free to find me at the break. Otherwise, enjoy the rest of your day.